Okay, 3.1 homework, exponential growth practice. Okay, so a nest of ants contains 600 ants. The population of the nest doubles every month. So we're going to write a formula using the number of ants, n, after t months. So we can say like n after t months is going to be, our initial is 600, we're doubling, and then t is going to be the number of months. And then the question is, how many ants are present after 3.5 months? So what is n at 3.5? Well, it's 600 times 2 to the exponent 3.5. Okay, so 6, 7, 8, 8. Here's the thing, there's decimal 22 here, but when we're talking about ants and population, there can't be decimal 22 of an ant. So just therefore, after 3.5 months, there are 6, 7, 8, 8 ants. Okay, number 2, the population of Numbersville is currently 4,000. Okay, so I'm actually, like when I skim this, I see that we have an equation. So that's good. 4,000 is our initial value. The population is expected to grow by 5%. So if we're talking about 5%, the growth is 0.05. However, every single year is going to grow by it's going to keep the 100%, and then it's going to grow by 5%. So 100% is actually denoted by 1.00. Okay, so 1.00 is our baseline. If there's no growth and no decay, it's just times 1, times 1, times 1. And then that's not exponential because we know that the base has to be between 0 and 1 or greater than 1. But it's not going to equal 1. Okay? Because that would be like the horizontal flat line. It would be the same number every single time. So we always compare it to 1.00. If it's a growth, we add that number. And then we're going to see later, if it's a decay, we would subtract that number. Okay? So each year for the next 5 years, the population P after the number of years n can be represented by this equation. So why is the base number 1.05 instead of 0.05? Because it's a growth from, and it includes the current population. Okay. Create a table of values showing the population growth over the next 5 years. Okay. So the population at time 0 is our 4,000. Okay. The population at time 1, we take that 4,000 and multiply it by 1.05, and we get 4,200. Then multiply that number by 1.05, and we get 4,410. Multiply that number by 1.05, okay, and we get 4630. It's kind of 0.5, so I'm not going to put it in here, but I'm going to leave it in my calculator, so like 0.5 as well, and then 1.05. So population, maybe someone's pregnant, maybe someone's, if it's like a club, population of a club, maybe someone's joining. Okay, and then times 1.05, we get 5105, and then that's it. Okay, so now we can go ahead and graph. So 0, 4,000, and this graph, pretend there's like a squiggly down there. Okay, after 1 year, there's 4,200 people. After 2 years, there's 4,410. After 3 years, there's 4,630. After 4 years, there's 4,862. And after 5 years, there's 5,100. So this is actually a curve, and it's going to continue to go. Okay, on this, we can say We can call this curve P, or we can call it P equals 4,000, 1.05 to the exponent n. Okay, we also have D and E. So D asks us to use our graph to estimate the population at year 8. So if we follow the graph up, and everybody might get like a different answer, it's approximately 6125. Okay, so using the graph, the population will be 6125. Let's say approximately 6125 at year 8. Okay, now E asks us to do the exact same thing, but actually use the equation. So the population is going to be 4,000 times 1.05 to the exponent 8. Okay, just note that it's difficult to actually pinpoint on a graph exactly where your exactly where the number is. So using that, I get 5909. So that's actually not too far off. Okay, I definitely overestimated here. So therefore, at 8 years, the population is 5909. Okay, a painting was bought for $475. Each year, its value increases by 8%. Okay, so we talked about how our baseline, so 475, if it stayed at that to next year, we would have 100% of the original value. Now, if it increases by 8%, we're adding 8% onto that. So now what we have is from the original price, now we have 108% of the original value, which is 1.08. So write an equation that models the appreciation value of this painting. So we can do value at time t equals the original times 1.08 to the exponent t. Okay, V is going to represent the value in dollars, and t is going to represent time in years. Okay, so the question is, how much is the value of the painting in 20 years? Okay, so that's just the value at 20 equals, and then we have this equation. Okay, so we have 1.08 to the exponent 20 times 475. Okay, so 2213.95. So 2213.95. We always stop at 2 decimals for money. Okay, so therefore, after 20 years, the value is 2213.95.